All right, good morning. I've updated some of the grades, not all of them. Your corrections I have not put in. And then the bonus, the sine cosine thing, I don't think I put in, but the other one that you did, I believe I did put in. Let me see if I have it. It looks like I left it on my desk with the others, but the grade should be updated, right? Okay. All right, thank you. All right, so today the plan is to finish off chapter 7 and start chapter 8, right? So this chapter 7, finishing it up, I'm going to try and go quickly, but I already know there's a couple things I want to do, so we might get a little bogged down, hopefully no longer than 30, 40 minutes, and then we'll start chapter 8, all right? So chapter 7, the last thing that we did, right, was those problems where we were trying to find the volumes where you had those cross sections, right? And now we're moving into the next section. Let me bring it up. 7.4, arc length. So look at that picture over there, right? Forget everything we've done in terms of like volumes and cross sections, all that. This is a brand new problem, right? So we have a curve, right? There it is. That looks like a sine curve, right? And we have a very simple question. If you were to take that curve and take it off the, imagine that curve was like a string and you were to pull that string tight like this, right? How long is it? Do you see that? Right, if you were to take that curve and just like imagine it's a string and pull it straight, then how long is that curve? That's called arc length, all right? Pretty simple concept, right? So the question is, how do we get to a formula that will give us the arc length? If someone gives us a function, any function, how can we get to an arc length formula? And what we're going to do to develop the formula is pretty much what we've been doing, which is to try and utilize the integral, right, to add things up. And so before I begin doing it, I want to, let me make sure I'm on camera here. I want to establish just a few things with notation that I'm going to need to prove this to you. The first thing is just to recall that it's going to be harder than I thought. I accidentally drilled into my finger this weekend, and I didn't think it would be that big of a deal, but I can feel this. Okay. So, all right, y equals, if we have y as a function of x, right, then when you say y prime, take the derivative, right, f prime of x, that's another way of writing it, but another way of writing it is just dy dx, right? Those are like 3 equal notations for taking the derivative. And what I want us to do is look at these two together, right there, as an equation. And since this is an equation, we're just going to multiply both sides by dx. So we get f prime of x dx equals dy. Anyone disagree? Or that seem reasonable to you? Okay, I'm going to need that. All right, I'm going to need that. So let's go back to that problem there. We have some sort of curve, right? Starts at some point A, ends at some point B here on the x-axis, some function here. We'll say, yeah, we'll just leave it like that. All right, there's our function. Now, if I want to know how long it is, what I can do is I can go try and look at just a tiny little infinitesimal little piece of it, right? This little tiny infinitesimal little arc, right? And try and figure out how long that is. And so I'd like for us to take that little, can you all see the little red piece there? Let's imagine we zoom in on this, right? We're going to zoom in into that piece. And what we're going to see is that arc, right? We're now zoomed in, right? Zoomed in, way in on this. And what I can see is that if I were to create a right triangle out of this, like this, right? Then you know how before when we were finding areas when this first started, we cut this up into a bunch of rectangles, vertical rectangles, right? And so the width of each rectangle was dx, right? So this piece right here that I zoomed in, you could almost look at it like it's not a rectangle because it's curved up at the top. But the width of it, right, this bottom piece should be dx. Y'all agree? That's your little change in x. And then the vertical change should be your change in y, dy. Infinitesimal little change in x, infinitesimal little change in y. Everyone buy that? So, I don't have a blue. You know what, there's a blue here. Let's see how good this blue works. So what I'm going to do is to figure out the length of this red. It's an arc, right? It's curved. I'm going to approximate it. I'm going to approximate it with a straight line. Now I'm going to have error, right? E-R-R-O-R. I'm going to have error in that, right? Like the length of the blue is not the length of the red. But when I do a limit, what happens is that this dx goes to 0, doesn't it? The width goes to 0. And wouldn't you agree that the smaller this gets, the more the error is reduced, right? And in the limit, when we have an infinite number of these, the error just basically vanishes to 0, right? We've been doing this, we did this with areas, right? We did this with areas as well. We had error, and when we apply the limit, it gets rid of the error. So I just need to know how long that blue is, right? How long is that blue? Well, Pythagorean, right? This squared plus this squared is that squared. Let's call this blue, let's call it L. Okay, we want to know, we want to know what L is. That's my lowercase l. All right, so what is L? L is, well, let's do Pythagorean first. We have dx squared plus dy squared must equal little l squared, right? Like that. And I can solve for L by taking the square root on both sides. So I get square root of dx squared plus dy squared equals little l. I did start recording, yeah? Yeah. I'm off today. Today, I've had a few off days, but I only got like 4 hours of sleep last night, so I'm a little, and the night before it was 4 as well, so I'm on 8 hours, 2 days. No excuses, I'm just saying. I'm just saying, like, I just feel a little off. All right, so we got it. We got a formula for L. And so what we want to do is we want to add these up, right? We want to add up this formula right here. So I know that I'm going to bring in the integral. I don't want to erase that. Let me put it here. So if I want the true length of the entire curve, L, then I'm going to need to add up, so integral. I'm going to start at A, I'm going to end at B, and then I'm going to add up a bunch of those, right? That formula. Okay, that's what we have, right? That's it right there. Just like when we had the cross sections, we came up with a formula for each of those cross sections last class. This is our formula. The problem with the formula as it appears is, you know that in all the integrals we've had up to this point, we've had like a dx or a dy out here, right, on the edge. We don't have that right now. So this is where I'm going to go back to this right here. Remember, dy is this, right? I'm going to replace dy with that. So let me, you know what, let's do it over here and then I'll bring it back here. So I'm going to say square root dx squared plus, okay, dy is actually f prime of x dx, but then all that squared, right? That's little l. And then that's the same as square root dx squared plus f prime of x, that thing, I'm putting brackets, squared, and then times dx squared. So I'm just squaring because there's multiplication here right between these. I just square each one of them, right? And then do you see these both have dx squareds, right? So I can factor dx squared out, So dx squared comes out. What's left when I pull that out of both of those? 1 plus f prime x, that thing squared, right? That's L. And then, again, you have multiplication. So you can take the square root of each of these separately. What's the square root of something squared? Well, they kill each other off, right? And you just get a dx. I got to come up here. So now we have dx, that's this, times, now the square root of this I can't do anything with. So I'm going to leave it. Square root of 1 plus f prime of x, that thing squared, right? Just like that. And then what I'll do is I'll push the dx to the back. And that's what L is. So now what I'm going to do is just come over here to this integral, and this integral becomes the integral from a to b of the square root of 1 plus the derivative of the function, that thing squared, and I'll put the dx in the back. Just remember the dx is not underneath the root, right? It's out by itself. And there it is. That's your formula. And I gave you all this handout, right? The color handout. This formula is on there. It's the second to last page? No, third to last page? Third to last page. It's called, it says arc length on top. If I say 7.2, I shouldn't say 7.2. I should say 7.4 on top. Okay, but that's the first formula right there on the top. You all got it? Okay, there it is. So if we want to find the length of a curve, right? If we want to find the length of a curve, then we have to evaluate this integral, which means we have to take the derivative of that function that we're given. We have to square that answer. We have to add it to 1 and take the square root and hope we can integrate that. Right? So generally speaking, arc lengths are not easy. You can't just take some arbitrary function and always find the arc length, because the integral might be hard. I'll show you as an example. That looks like the sine curve, right? Let's try that. Let's try to see if we can find how long that arc is. All right, so example, let's find the length of y equals sine x on the interval 0 to 2 pi. Are you all understanding? I think I asked you this last time. Are you all understanding how this integral is just a tool? I mean, I've referred to it as a tool now several times. It's just a tool, right? It helps us add things up. What we're adding up depends on where we are, right? Depends on what you need to add up. All right, so here we go. This is our function, right? So this right here is our function of x, right? This is our function of x right there. And so I'm given the interval 0 to 2 pi. So before I begin doing any work, right, before I go after that integral, I'm going to do some scratch work here on the side, right? I need to take the derivative. I need to square it, right? So I'm going to do that. That should be pretty straightforward. Scratch work. So I'm going to say f of x is sine x. And then I need the derivative, which is cosine x. Not too bad. I need to take that derivative and I need to square it, which is cosine squared. Okay, that's all good, right? So now I'm going to come over here and set up this integral. This integral, the length I'm looking for, capital L. I called it capital L, right, instead of little l. Little l was the little pieces we were adding up. Capital L is the sum of all of them. Okay, so this should be the integral from 0 to 2 pi, given to me, and then square root of 1 plus the derivative squared, which we just said was cosine squared x, dx, right there. Now, if that was a 1 minus, right? If that was 1 minus, this would be great, wouldn't it? Because what's 1 minus cosine squared? Sine squared. And then the square root of sine squared would just be sine. But it's not minus, right? It's plus. And so now we start going through all of our techniques, right? Basic U substitution. Well, I see a cosine x. I can't let that be u because the derivative of that sine x, I don't see as sine x. Integration by parts, not going to happen. Trig integral, nothing. We don't have anything for this, all right? We have nothing for this. So we can't do it. Now we could go to like Wolfram alpha or something. We could try that. You want to try that? Let's do that. So I'm going to have Wolfram do this for us. I'm going to go integral 0 to 2 pi, and then square root of 1 plus cosine x squared with respect to x. And yeah, it's definitely going to give us an answer. What does it give us? Oh, can y'all see that? Sorry, it's not very big. You see it right there? 7.6404, right, is the length. Now it says approximately. See the squiggly equals? That's only because it rounded, okay? I could ask it for more digits there on the side, you see? See how I can ask for more digits? That'll give me more accuracy. There we go. Oh, shit. It gave us a lot more digits. I didn't want that much. But see, and I can ask for more. I can ask for more, and it'll be more accurate. So what's happening here is like, why can the computer do it and why can't we, right? Well, the way the computer is doing it is it's using series. It's using what's called Maclaurin series or Taylor series to do this. That's chapter 8. That's what we're going to do in chapter 8. But we are not going to do that problem. We're just going to develop the idea and then say, okay, yeah, this is the way a computer would utilize this idea. Does that make sense? So when we type it in. Now, if I were to remove the limits of integration, because remember this, when you have limits of integration, you should get a numerical answer, right? But if I remove the limits of integration, then I just want the indefinite integral, right? Which is just some function. It should just spit out a function plus c. Let's see what Wolfram does with that. What do y'all think? Think it's going to be okay? Let's see if Wolfram can do it. I don't know what's going to happen if I leave those blank. Yeah, it wants. Let me see. I think I'm going to have to start over. Will it replace it? Yeah. Yeah, you know what? By the time I'm just going to start over. Yeah, there we go. So square root 1 plus cosine x squared dx. All right. Let's see what it does. Okay, it gave us something, right? You see this? But what is this capital E thing? Capital E with an x with a bar with a 1/2. What the hell is that? Well, E with x with a bar and then m is the elliptic integral of the second kind with the parameter m equals k squared. What the? Okay, so what this is telling you is that, yes, Wolfram can give you an answer, but it's not giving you a nice function, is it? It's giving you some weird thing we've never seen before. That means it can't really be done by hand, all right? You cannot do it. So this series that we're going to study, what they're going to be important for is for things like definite integrals, which in the real world is normally what we are looking for. You know, this might actually be the length of something, and we want to know that numerical answer. So the series will allow us to do that. So I hate to give you an example we can't do as your very first example, but I want you to see just how this idea of needing to do the derivative and then, oh, I forgot to put squared here, everyone, sorry. Then we square it, then we put it under here, and we add 1, we take the square root, and we hope we can integrate it, right? We hope we can. So on your homework, you'll have some problems, and I'm going to do one more example, but in your homework, I'm kind of leaving you to see how it works out, all right? I can tell you the algebra is going to be a little bit messy on some of the problems. Some of them are easy, some of them the algebra is a little messy, but you can watch my videos to see how I do that. But generally speaking, again, this is not easy to do by hand. So let's do something fun, at least fun for me. I don't know if you'll find it fun. But we've proven something in here in this class that I think y'all liked. Remember we proved that the area of a circle was pi r squared, right? So if you go back in your notes, recall that we actually talked about this. If you're given a circle of radius r, I think we used capital R most of the time. Capital R is our radius. We've already proven here that the area is pi r squared, right? We proved it though. We used the actual area, and I think it was a trig sub, and we had to do some stuff, but we got that. And then when we did the wrapping around, didn't I prove to you the volume of a ball, like a volume of a sphere, right? We also proved that if you were to take this top region, wrap it around, you get a sphere, and we proved that the volume of this was 4/3 pi capital R cubed. So I'm putting check marks here. Didn't we prove that? Yes? Okay. So what I'd like to prove now is what the circumference of a circle is. See, this is arc length, right, that we're talking about. That's the length around something. So I'd like for us to prove that the, where are my notes? Okay, there's the formula, a little bit. There's my formula up there on the board. Okay, so what I'd like for us to prove now, let's prove let's just say this. Let's prove that circumference equals 2 pi. I'm going to say capital R instead, right? For this circle, let's prove that the circumference is 2 pi r. We all agree with that, right? 2 pi r, we've been taking that on faith for a long time. Let's prove it. So the way to prove it is I'm going to take the circle and remember this. That's the equation of that circle. We've done this twice before, so I don't want to spend too much time on this. We solved it for y, and we got square root r squared minus x squared. That right there, this is the function that draws the top half of the circle. Now, that's me just solving for y, right? And remember when you take the square root, there's plus or minus. The plus draws the top half of the circle, the minus draws the bottom half. We just looked at the top half though. So do you all agree if I could find the length of this green, then double it, I should get 2 pi r? Yes? Yeah? Okay, I'm gonna go one step further. How about we do this? Instead of finding the length of the green, can we just find the length of the red and then multiply that times 4? And that should give us 2 pi r, hopefully. Anyone have a question as to what I'm doing? No? Okay, so if I want to know what let's just find, I'm just focusing on the red right now. To find that, I need to know what the function is. I'm going to do some scratch work because I want to set up that integral. I need to know what the function is. Well, the function is the square root of capital R squared minus x squared, right? Remember, capital R is a constant. We have to take derivative of this. The derivative of this function, okay, well, careful here. How do you take derivative? Chain rule here, right? What's the derivative of the square root of something? 1 over 2 square roots of whatever's there, right? Not done though, right? Times, now derivative of what's in here with respect to x, meaning r is a constant, right? What's the derivative of a constant squared? 0. Minus, what's the derivative of x squared? 2x. So minus 2x, like that. That's the derivative of that function. Let's clean it up. Move this up top. Those 2's will go, right? You'll have negative x over square root of r squared minus x squared. Y'all agree? Okay, that's our derivative. What else do we need to do? To get in that formula, we're going to need to do what with that? Square it first, then add 1. So square that, right? In the formula, we have to square it. So if we square this, if you square this, you just square the top and bottom, don't you? Square the top, you get x squared. Square the bottom, the root goes away, right? Like that. There it is. I squared it, right? So when you square it, when you take this and square it, the negative will go. Yeah. Everyone got that? Okay. So now I'm going to go set up my integral. All right? Set up my integral. So here's my picture. All right, I'm doing the red curve. Where does it start? 0. Where does it end? That's a unit circle. Careful. What's the radius of this circle? What? The radius. How far is from here to here? What are we calling it? Capital R. Right? Capital R. Right? We're going from 0 to capital R. All right, so ready for the integral? The length of this red piece, okay, the red piece only, the length of it should be the integral from 0 to capital R of the square root of 1 plus what we just got over here. This. Dx. Now that integral looks terrible, doesn't it? When you look at it initially, you're like, yeah, there's no way we're doing that, right? But it actually is not too bad. All right, let's just keep going. What I'm going to do, and this is a technique you'll use in your homework as well, is when this is not something easy and you've got 1 plus a fraction, get a common denominator, put those together. So turn the 1 into a what? R squared minus x squared over r squared minus x squared. Okay, so this will be length equals integral 0 to capital R, square root of, okay, this will become r squared minus x squared over r squared minus x squared plus x squared over r squared minus x squared dx. I didn't have to show that step, did I? I'm going to anyway. All right, equals integral 0 to capital R. Okay, square root of. All right, when we put these together, right, they'll have the same denominator. What does the numerator turn into? Capital R squared, right? That's it. The x squareds cancel. And now you have a single fraction in a square root. So you can do the square root of top and bottom separately, can't you? Right? So this will become integral 0 to r. Okay, you take square root of capital R squared, that gives you just r. And on the bottom you have square root of r squared minus x squared dx. Almost there. Who has questions? Y'all are looking at it like I'm writing in some foreign language up here. You all right? Okay. R is a constant, right? Okay, so I'm going to pull the r out of the integral. Capital R. That r is going to go out front. 0 to capital R. 1 over square root capital R squared minus x squared dx. What do you think? It's trig sub. Exactly. It's trig sub. But we have a formula for it. For this particular case, can I look? We have a formula. It's on the integral page, so reference page 6. It is, where is it? 16. Formula 16. This is like 1 over the square root of a squared minus x squared. So R is the A. R is the A. That's what, that formula 16 is what we would get if we did trig sub. So we're not going to do trig sub because we have the formula, all right? So this becomes, okay, capital R times, now the antiderivative of that, according to that, is inverse sine of, yeah, so for us it'll be what? What's our variable? X over, what's A for us? R. So from here to here, this is formula number 16. And then that's the antiderivative. We still need the fundamental theorem, so I need to go from 0 to capital R. All right, we're almost there. Now we're going to plug in the two endpoints, right? The R and then the 0 and subtract the answers. So we should get two things, something minus something. The first one, when we plug in, we get, let me give myself some more room. When we plug in capital R, we get R times inverse sine of R over R. And then we have capital R inverse sine of 0 over R. Like that, right? All right, let's do the easy one first. This right here is sine inverse of 0. So that is saying, what that's saying to you is, remember, sine on the unit circle is the y-coordinate on the unit circle. So it's asking you, when is the y-coordinate equal to 0? When your angle is 0, right? So this is 0. And so this whole thing goes away. Now the other one, right? Pardon me? Sine's the y-coordinate. So when you're at 0 angle, your y-coordinate is 0. Right? Yeah. We're about to do what you're saying, I think. This is really saying sine inverse of 1, right? Because capital R over capital R is 1. Okay, so now you're saying where on the unit circle is your y-coordinate 1? Straight up, right? Pi over 2. So this right here is pi over 2. And so you have capital R times pi over 2. So your answer is pi over 2 times capital R. And this was just the red, right? This was just the red. Right? So if we want the circumference of the whole circle, we have to multiply that times 4. So 4 times that gives us, right? 1, 2, 3, 4, 4 of them. Pi over 200, that equals 2 pi r. There we go. So we just proved a formula that you've been using for a long time. Pretty cool, huh? All right, so that's it. I'm not going to go any further with this. You have